Okay, good morning, everyone. The attendees are very less, but still we will start the lecture. What we have seen in the last lecture that we will discuss first, and then we will go for the next one, right? So, step up chopper and step down chopper. These two already we have seen in the last lecture. Now we'll see the step up down chopper. Before that, I'll just again want to recall the step up chopper in the short, and then we will go for the step up down chopper. Okay. So in a step up chopper, you can see here the switch is connected parallel to the load and a battery. Then diode D that is connected in series with the load. Okay. Then inductor L. So what happens when the switch is closed? When switch is closed, then when switch is closed, then current flows from battery EDC L, then chopper, or you can say switch EDC minus, right? So this time, during this particular on time of a switch, the inductor store the energy in its magnetic field with the polarity, this one positive, left side as a positive with respect to the right side, right? So this is the energy stored by inductor. Now maximum energy stored by inductor is equal to EDC. Okay, the energy stored by inductor is depends upon the on time of chopper. So if your on time is very less, then inductor stored energy is also very less. If the on time is max, then the maximum voltage will be stored by the inductor, and that is equal to the EDC. Right. So when the switch is off, see, if switch is on, that time the inductor store the energy, but the load current or load voltage basically is equal to zero. Load voltage is equal to zero, right? So during on time, output is equal to zero, and during off time of a switch, no current flows through the switch. So what happens? This particular inductor acts as a battery, right? This is the stored charge by inductor L, and this EDC comes in series with the inductor energy, right? So these two batteries comes in series. This is actually EDC, okay, and this is the inductor energy. So these two inductor energy is maximum equal to EDC, right? If the T-on is larger, then the energy stored by inductor is large. Okay, so these two batteries comes in series. So the total voltage will appear across the load because diode is forward bias. So that voltage is equal to twice EDC, right? Maximum is twice EDC, but there are some losses across the inductor itself. So the energy stored by inductor is always less than EDC, but ideally we can say the energy stored by inductor is equal to EDC. But practically it is not possible. So practically the energy stored by inductor is less than of EDC. So total voltage is always less than of twice EDC. So this is step up chopper. When switch is on, output voltage 0. When switch is off, that time output voltage is equal to EDC plus inductor energy, that is LdI by dt. So that is the working is given here, right? Then this is output voltage is equal to ADC plus LdIs by dt. The total power that is fed or maybe stored across input power that is given to the inductor is equal to EDC into IS into T-on. This T-on is important. As your T-on is less, the input power is less. If T-on is more, input power is more, because EDC is a constant, so IS is a constant. Only T-on is a variable in this particular input power. So as your T-on is larger, the input power is larger, right? So this is the input power. During the on time when chopper is on, the energy input to the inductor from the source is given by Wi equal to EDC into IS into T-on. Now, during T off, when the chopper is off, energy released by the inductor to the load is given by W0 E0 minus EDC into IS into T off, right? So again, E0 is nothing but the energy stored by inductor plus EDC, right? So if you want to calculate the energy across inductor, then total output voltage minus EDC into IS into T off, you will get a output power. Okay, so this input power, if you consider that the system is lossless, then input power is equal to output power. So input power WI equal to EDC into IS into T on, and output power E0 minus EDC into IS into T off, right? Then from this first equation, E0 equal to EDC T on plus T off by T off. Okay, so this T on plus T off is nothing but a T, right? And T off nothing but a T minus T on. T off. Okay, so when we take a T as a common, then we will get a 1 divided by T minus T on by T. T by T nothing but a 1, and T on by T is nothing but your alpha. Alpha is a duty cycle. T on by T nothing but a duty cycle, right? So E0 equal to EDC divided by 1 minus alpha. For alpha equal to 0, you will get E0 equal to EDC. And if alpha equal to 1, then E0 equal to infinite. When alpha equal to 1, when T on equal to T, that time alpha equal to 1. And when alpha equal to 0, when T on equal to 0. If T on equal to 0, alpha 0. And that time the output voltage equal to EDC. And if alpha is greater than 0, then E0 is also greater than EDC, right? So as you vary the alpha, you will get a variable output voltage. Then step up down chopper, next part, step up down chopper. Okay, now in this particular chopper you will get a lower voltage as well as higher voltage. Okay, so see the figure, the switch is connected in series and inductor connected in parallel and diode is in reverse direction, right? As like in a previous, if you consider, so it will be a reverse direction, right? So see, the working is very simple. The chopper can also be used both in step up and step down modes by continuously varying its duty cycle. As already we know that in step up chopper, if alpha equal to 0, you will get a EDC, E0 equal to EDC. And if alpha is greater than 1, then you will get a E0 equal to greater than of EDC. Okay, it depends upon again a duty cycle. If duty cycle is maximum, that is equal to 1, then E0 equal to infinite. Already we have seen, right? So the principle of operation is illustrated in figure above slide, shown in figure output polarity. When the chopper is on, what happens in this particular circuit? See, if chopper is on, if the chopper is on, then if chopper is on, then current flows, supply current flows through the path, that is EDC plus, then chopper, then L, and then EDC minus. See, EDC plus dash chopper dash L dash EDC minus. Hence, the inductor L store the energy during the on period. So inductor store the energy during the on period, right? When the chopper is off, the inductor current tends to decrease. Inductor current tends to decrease. As a result, the polarity of EMF introduced across L is reversed. What happens already? We know that every time when the switch is on, then the current flow like this. That time inductor store the energy in its magnetic field with the polarity upper positive, lower negative. But as soon as you turn off the switch, what happens? Immediately the polarity of this stored charge get reversed. So downward is a positive with respect to upward. So current start to flow from inductor. Inductor start to lead the energy through the load to the diode and back to the inductor, right? So when chopper is off, the current flows from L plus minus load dash load dash L dash D dash L minus, right? So L minus is this one, L plus is this one, L plus load D L minus, like this. Okay, so during the on period, the energy stored in the inductance is given by Wi EDC into IS on, as like a previous one. Now for lossless system, if we consider that then E0. Now this time just a small change in the figure. W0 is a different. E0 is a totally depends on the inductor energy only. It is not depends on EDC because EDC, when switch is on, diode is in reverse bias condition. So current flows only through the inductor, not through the diode, right? Because of this reverse bias diode. So current flows from this switch to inductor back to the EDC minus. So whatever energy stored by inductor, only that energy delivered to the load. Okay, so that W0, the power, that output power of inductor is equal to E0 Is into Tf. This is a small difference, right? In previous equation, what we have seen, E0 or W0 equal to E0 minus EDC into Is into Tf, right? But this time the W0 equal to E0 into Is into Tf, right? Again, if we consider the system is lossless, then input power equal to output power, right? So input power equal to output power. So EDC into Is into ion, actually Ton, not ion, it's a Ton, equal to E0 Is into Tf, right? Or you can say E0 equal to EDC into Ton by Tf. EDC into Ton by Tf, right? Now, it is E0 equal to EDC, Ton as it is. Now we replace Tf equal to T minus Ton. We are replacing Tf with a T minus Ton. So we'll get again same, that is 1 divided by T by Ton minus Ton by Ton. So Ton by Ton is 1 and T by Ton is nothing but 1 by alpha, right? So Ton by T nothing but alpha. So we get a E0 EDC, that's our as it is. T by Ton is 1 by alpha and Ton by Ton is 1, right? So E0 equal to EDC alpha divided by 1 minus alpha. 1 minus alpha, right? Now, in this particular equation, if you put the alpha equal to 0.5, or we can say from 0 to 0.5, the step down chopper operation is achieved, okay? Because E0 equal to EDC into alpha divided by 1 minus alpha. So if we put alpha equal to 0.5 divided by 1 minus 0.5, so it is a 0.5, 0.5. So you will get an output equal to EDC, or E0 equal to EDC, or less than of EDC, right? But if alpha is equal to greater than 0.5 to 1, just put the value of alpha equal to 1 in above equation. So we will get a E0 equal to EDC into 1 upon 1 minus 1. So 1 minus 1 equal to 0. 1 upon 0 is infinite. Infinite into EDC is equal to infinite. So E0 equal to infinite. That is definitely greater than of EDC. So this equation itself shows the operation from 0 to 0.5, it acts as a step down chopper, and from 0.5 to 1, it acts as a step up chopper, right? So this is about the step up down chopper, okay? So if anyone having any doubt in this step up down chopper, you can ask me. I'll just give you 1 minute. After that, I'll go for the next part or next topic, right? So already we have seen 3 different choppers. Step down, also called as a class A chopper or first quadrant chopper. Then step up, also called as a class B chopper, also called as a step up chopper. And this is a step up down chopper, right? So the third chopper is called step up down chopper, or you can say variable chopper. So all 3 choppers already covered. If any doubt in step up, step down, or step up down, you can ask me. Otherwise, we will go for the next. So just give 1 minute. Otherwise, we'll go for the next topic. If you are having any problem, you can ask me. You can even ask your questions in a chat box so that I can give your answers or maybe answer of your questions. If you don't have any query, then we will go for the next part. This chopper is nothing but a power switch. Okay, so power switch is there If you are using power switch, it means that definitely triggering circuit is required, then protection circuit is also required, and even for a chopper, commutation circuits are also required if you are using SCR. So that part is not shown here in the figure for simplicity. But you have to consider while explaining, while designing the only by using switch you cannot achieve the step up or step down approach or maybe the output, right? So you have to use a power switch, that is electronic switch. Okay, so it is called basically electronic switch. Okay, so not a mechanical switch, it's an electronic switch. So use a proper power device. If you are using BJT, if you are using MOSFET, IGBT, then there is no need to use commutation circuitry because these devices are easily turned off by simply removing the base current or base voltage or gate voltage. In case of power transistor, you simply remove the base current, automatically your power transistor turns off. In case of MOSFET or IGBT, you just remove the gate voltage, your MOSFET automatically turns off. But in case of thyristor, it is SCR, it requires a commutation circuitry to turn off the thyristor because this is actually a DC operation because we are using battery DC voltage. So on a DC voltage, once your thyristor turns on, SCR turns on, it remains on because it is a latching device. So once it turns on, it remains on even the gate bias is removed. If you remove the gate bias, still your SCR turns on because once the voltage is greater than forward breakover voltage and if anode current is greater than latching current, your device remains on even the gate bias is removed. Already we have seen the latching current, holding current. So in a latching current, we already discussed that if the current is greater than latching current, then your SCR remains on even after gate bias is removed. So if you want to turn off the SCR, you require some additional circuitry called as a commutation circuitry. Without commutation circuitry, you cannot turn off SCR in a DC circuits. So that circuit is also not shown here for simplicity because our aim is to learn the basic concept of choppers, not the actual total circuitry because the protection circuits we already learned, the gate drive circuits we already learned, even the commutation circuit is not a part of your syllabus, but commutation circuitry is by commutation circuitry. So I'll just explain one example. Whatever the anode current, if that current is less than holding current, right? If you are using SCR and in SCR, if the anode current is less than holding current, then your SCR turns off. Okay, so we have to minimize the anode current below holding current, then your SCR turns off. So this is the one of the method of commutation. Okay, so in commutation, simply minimize the anode current, or second method, you can directly apply reverse voltage across the SCR, then your SCR maybe turns off, right? So these are the some commutation methods. So any one method is used in the circuit, but all the circuit complexity, to avoid the complexity of a circuit, the gate drive circuit, then protection circuits, and even the commutation circuits are not shown in the figure. Okay, so is there any question you can ask me? Otherwise we'll go for the next. Next is control strategies. Okay, next is control strategies. So in this particular control strategies, already introduction of these control strategies we have seen, right? So there are two main methods. At the time of introduction, I already told you what are the methods used in a chopper, but it is a part of your syllabus. So we will discuss in details. So control strategies means what? You have to control the output voltage of a chopper. Okay. So to control the output voltage of a chopper, we have to control the on time, off time of a chopper. Okay. So how to control the on time off time? So for that purpose, in a chopper, there are two methods used. One is called time ratio control, that is a TRC control, and second one a current limit control. These are the two methods used in a chopper to control the output voltage of a chopper. Okay. So first one, time ratio control. So in which the T on by T is varied. This is affected in two ways. There are variable frequency operation and constant frequency operation. So already we discussed about this. That is variable frequency and constant frequency operation. Uh, what is the variable frequency and constant frequency operation? Basically, time ratio control, it means T on by T is controlled. Okay. So out of that, you can control T on, right? You can vary T on by keeping frequency constant. It means T constant, or you can keep T on constant and change the total T, that is a frequency. Okay. So getting or not, what is the meaning of this time ratio control? You are controlling the T on by T. So in this particular equation of a duty cycle, uh, T on kept constant, and by changing T, total T, you can control the voltage. That is the first one, called as a frequency control. And second one, by changing T on, keeping frequency constant, it means total T constant, that is called as a constant frequency system. So there are two systems, constant frequency and variable frequency. Okay. So this first one is a constant frequency, in which the time, total time is maintained constant. T on plus T off is equal to constant. But T on changing, right? So if T on changing, it means automatically T off also changes. But overall time T on plus T off is equal to constant. Okay. So you can see here in the figure, first one, sorry. In this figure, first figure, uh, T on is a smaller, T off is a larger, but you can check the time T, right? If you compare with the second figure, T on increases, T off decreases, but total time remains constant. Time is constant, right? So T constant, only T on changes. This is called as a variable on time, right? Constant frequency. Sorry. Constant frequency system, in which on time varies but total time is kept constant. And second one, variable frequency, in which you can check here T on, okay, then T off. So every time the total time period basically changes, right? Constant T off means constant T on. So something is constant, but time, total time will be changes. Okay. So in the first figure, you can check T on is a smaller, right? And T off is a larger. In the second figure, T on kept constant, but T off is a smaller. Right. So in the first figure, this is a total T up to this one, right? And in the second figure, total T is this one. So that is a called constant T on, and second is a constant T off. So we can check here, T off is a constant, T on is a smaller here, T on is a larger here. Okay. So this is called as a variable frequency, and in which you can keep any one constant, T on constant, then change T off, or T off constant, change T on. If you change T on and keeping T off constant, then also your frequency changes. Or you can keep T off constant, T on variable, then also your frequency changes. So that is called as a variable frequency. Kept any one constant and other is variable. So overall time is changing. If time changing, it means that the frequency is variable. So this is another method. There is some disadvantage of this particular frequency modulation, or you can say second method, major disadvantages compared with the pulse width modulation. So chopping frequency has to be varied over a wide range of control of output voltage in frequency modulation. Filter design for such is something. So these are the some disadvantages which are given in front of you, right? So this is for your reference. Next one is uh, current limit. This is another method in which the two levels of a current is compared, and according to that the triggering pulses will be generated. You can check here in a figure. This is the current value, I max, I minimum, right? So whenever the current level is greater than IO max, then the switch turns off, right? And whenever it is less than the IO minimum, then switch again turns on, right? It turns on up to the current increases greater than IO max. So between the two levels of a current, it is compared, and according to that, the pulses are generated. These are the pulses. If the current on time is like this, right? So on time maybe increases. So the pulse or maybe the current waveform generated, and according to that the two levels, comparison of two level, IO max and IO minimum, according to that the pulses to the switch is generated, right? So that is called as a current limit control. In current limit control strategy, the chopper is switched on and off so that the current in a load is maintained between two limits. Okay, so according to the requirements of a load current, this current limit control method is used. When the current exceeds upper limit, the chopper is switched off. During off period, the load current freewheels and decreases exponentially. When it reaches lower limit, the chopper is switched on. Current limit control is possible either with constant frequency or with a constant T on. The current limit control is used only when the load has energy storage element. It means that this current control method cannot be used with a resistive load. This current limit control cannot be used with a resistive load. It can be used only with inductive load because inductors store the energy, right? So energy storage element is required in a circuit. Otherwise, current limit control method cannot be used. So this is particularly used with inductive load only. The reference value are the load currents or load voltage. Figure next slide illustrates the principle of current limit that is shown here. Since the chopper operates between prescribed current limit, discontinuity cannot occur. The difference between IO max and IO minimum decide the switching frequency, right? So this is about the current limit control. Now next one is chopper configuration. Okay, chopper configuration. In this particular chopper configuration, uh, already I discussed about the classification of a chopper, in which the classification depends upon the operation or direction of voltage and current, that already we discussed. So the next classification is based on the direction of current and voltage, that is first quadrant, second quadrant, two quadrant, four quadrant, and so on. So this particular graph uh, figure illustrate what is the application of that particular chopper. That is most important. So in a chopper one, or you can say class A chopper or first quadrant chopper, right? This is called first quadrant or class A chopper. Okay, so first quadrant or class A chopper, in which the output voltage is positive and current is also positive. Output voltage is also positive and current is also positive. So such type of chopper is used for drive motor, right? Motor driving, or maybe to turn on or to drive the motor. Because to drive the motor, the voltage and current both should be positive. Okay, and only in this particular configuration, the voltage as well as current both are positive. So chopper class A chopper or first quadrant chopper is used for motor driving. Okay, then class B chopper, this class A chopper is also called as a step down chopper. Keep in mind, class A chopper, step down chopper or first quadrant chopper, तिघांचे सर्किट सेम आहे, फक्त नाव वेगवेगळे आहेत. Okay, so operation in lies in first quadrant, so it is called as a first quadrant. It is also called as a class A chopper, right? And it is also called as a step down chopper. Okay, so all three choppers, nothing but the first forward, that is first quadrant chopper. Then second quadrant chopper, also called as a step up chopper, in which the voltage is positive but current becomes negative. So this is used for forward braking. This is used for forward braking. First is driving, second is braking. Okay, so this is called forward braking, right? Then third quadrant, in which the current as well as output voltage both are negative. So it is called reverse drive. If you want to drive the motor in reverse direction, then voltage as well as current applied to the motor must be negative, right? And so that this particular third quadrant, if you want to drive the motor in reverse direction, you can use this particular third quadrant chopper operation. And in a fourth quadrant operation, that is called reverse braking, reverse driving, reverse braking, right? Forward driving, forward braking. So these are the applications of the chopper. Motor तुम्हाला ड्राईव्ह करायची आहे, रन करायची आहे पुढे जायला, तुम्हाला तिला ब्रेक लावायचा आहे, तर त्याला फॉरवर्ड ब्रेकिंग म्हणतात. सो यू कॅन block the speed of motor simply by reversing the current and so on. So this is just for introduction purpose. Now first quadrant chopper, also called as class A chopper. First quadrant chopper is also called as a class A chopper. Okay, so this in this particular chopper, with a RL load that is given, so motor is your load. So in this figure you can check this figure already we have discussed as a step down chopper. So first quadrant chopper or class A chopper or step down chopper, all three choppers are same. So I will not explain this first quadrant chopper again, already we discussed. So again, for your reference, I have given the theoretical part in the slides. Then second chopper, also called as a class B chopper, right? So this chopper is also called as a step up chopper. So already we have seen step up chopper, nothing but the class B chopper, nothing but the second quadrant chopper. Okay. So again, the information is given for your reference. Now I'll directly go for the two quadrant chopper. Okay, that is called class C chopper. You can check here in this chopper what is basically disadvantage of these two choppers, because if you are using the chopper A or class A chopper for motoring and class B chopper for braking, then definitely there are some disadvantages, right? So these disadvantages are given here. If the chopper is turned on and off during a regular interval of a T1, the EMF EB, back EMF EB, store the energy in inductance L. Whenever chopper is conducting a part, that stored energy is delivered to the source EDC by current through diode D2 when chopper 2 is commutated, right? Therefore, when chopper is on, E0 equal to 0. When chopper is off, then diode D2 conducting, E0 equal to EDC. Okay, but this configuration is used for regenerative braking of DC motor. A typical application is subway train. Already I told you that the DC motor used in a railway. So forward braking and reverse braking, sorry, forward braking and forward driving. So to drive the motor in forward direction, the class A operation is performed, and whenever the braking is required in a railway, then class B operation is performed, right? So basically there are some disadvantages. Through switching from class A to class B configuration, it is satisfactory method to obtain regenerative braking for some application. But in application like machine tool drivers, a very smooth transition from driving to braking is essential, and this requires uh, the drive is provided by connecting type A and type B in parallel. Okay, so class A and class B. Class A chopper, also called as a first quadrant chopper, is normally used to drive the motor in forward direction, right? And this class B chopper that is required to drive the motor in braking, that is called, maybe you can say, reverse bias direction, so that automatically the speed of motor decreases. Okay, so this type of methods are already used in a subway train, or maybe a simply train, you can say. So class A operation is performed to drive the train in forward direction, and for braking in a train, the class B operation is performed. So such type of operation is possible in a railway or other operations, but in some applications where smooth transition from drive to braking is required. Now in railway there is no need to use smooth operation, right? But in some applications, like machine tool drives, in which a very smooth transition from driving to braking is essential, and that time the switching from class A to class B is very difficult. So definitely there are some disadvantages. That's why the class C amplifier, sorry, class C chopper is invented, or maybe given, so that a smooth transition from driving to braking is possible, right? So this two quadrant chopper we will see in the next lecture. So last 1 minute is remaining. You should give your attendance in a chat box. uh, give attendance only once, don't give attendance 2 3 times. Okay. Uh, After this, there is a one chopper called as a four quadrant chopper, and then the fifth unit is over. So we will go for sixth unit. During Diwali, I think only 14, 15, and 16 is holiday. So other days, your regular lectures will be conducted online. So in the next lecture, that is on 9th, uh, we will see two quadrant, and maybe up to the 10th we will cover the unit number 5, and we will start unit number 6 in maybe on 13th November. I think 6th December is the last date of a syllabus completion. So we will complete the last unit, because last unit is very simple. Only the applications, actual applications of the power devices or the circuits uh, used. So we have to see the applications of inverter, applications of chopper, then applications of converter in a last unit. So very simple topic there in the last unit. So we will see the unit number 6 from